Hello, welcome back to Math 253, Calculus 3 here at Cañada College. My name is Lapuz, and in this video we're going to take a peek at section 2.3, the dot product. In this section we're going to take a look at the definitions, establish some angles, projections, and then some applications of the dot product. First, the definition is going to be given in an algebraic form or symbolic form, where we've established using components, then the dot product of two vectors is essentially the sum of the products of each of the components. So if you have u1, u2, u3, and v1, v2, v3, the dot product of u and v is going to be u1 times v1 plus u2 times v2 plus u2 times v3. The dot product comes with a handful of properties that we can prove, that the book proves, or the book proves some of them, and you're going to be asked to prove some of the other ones. But the dot product is commutative. There is a distributive property that goes with addition. Associative property applies only if you're going to multiply by a scalar. If you have a dot product multiplied by a scalar, then the scalar can be associated with the first vector or the second vector. Notice if you try to take the dot product with three vectors, that doesn't make sense. Finally, another important property of the dot product is going to be, they call it the property of magnitude. And if you dot a vector with itself, it's essentially the magnitude squared. You can visualize that if you want, but if you write it down, it'll become pretty clear. Another important aspect of the dot product is the angle. Some books call this a definition, some a theorem. In this particular text, it's a theorem that probably should be proven, but we're not going to prove it. In any case, the dot product turns out to be equal to the magnitude of each of the vector times the cosine of the angle between them. And so there's a set angle between them. You could actually imagine two angles between two vectors, but we're looking at the angle that's less than 180 degrees. Now, if your angle happens to be an acute angle, less than 90 degrees, then the cosine of an angle that's less than 90 degrees is positive. But if your angle is an obtuse angle, that's an angle that's bigger than 90 degrees, then the cosine of that angle will be negative, and therefore your dot product will be negative. So that's an interesting aspect of the dot product that could be important when you're expecting a positive or negative value depending on its angle. Another important aspect of the dot product tells us that a cosine of 90 degrees is 0. So if your dot product turns out to be 0, then that means the angle between them has to be 90 degrees. And that is an important aspect of the dot product, is when we can figure out when things are perpendicular to each other. They call it orthogonal. That is to say that they're perpendicular. Next, let's study some projections. So a projection of one vector onto another is going to be given by this formula. And the formula, well, in this case, they call this the magnitude of the projection. And so there's actually two aspects to projection. There's a vector projection and a scalar projection. Given here is a scalar projection, which is the length or the shadow that one vector makes onto another. So this is our given formula. But to get that picture, we can see that vector v being projected onto vector u. The length of that new vector, it's going to be symbolized as proj u v, or we can say that as a projection of v onto u. And so that is given by that formula. And we can prove this using just some basic trigonometry. This will be important for us to find distances, to find lengths of things, and just in general, projection becomes an important aspect of studying both calculus and linear algebra. Finally, we're going to apply some ideas behind the dot product with work. It turns out that work, which is what we knew as force times distance, is very intimately related with vectors. So a force of, let's say, 8 pounds, we're pulling a wagon at some angle, 55-degree angle, pulling it upward towards us. And if we're going to move this wagon 50 feet, the amount of work that it's going to take is actually going to be just simply the dot product of those two vectors. Now, we have to find the components of that vector that pulls towards you, the 8-pound vector that makes an angle of 55 degrees. But we can do that. Hopefully we can do that and be able to make the computation for the work. All right. That is our quick overview of dot products in section 2.3. Good luck.